So this is going to be challenging because we're going to do a deep dive in less than an hour. So how about that for a challenge? And we're going to take a look specifically at 802.15.4. And I believe when we look at IoT devices that are out there, you'll find that about 60% of devices are actually using this protocol. So it's a really important protocol to start understanding. So Heather said to me, make sure you brag a little bit about yourself and explain why you should listen to me. So I leave you to read this, but I just share with you, I first worked on this standard prior to it actually being finalized in 2001, when we were putting in sensors into clothing to be put on premature babies so they could be monitored, potentially wireless. So I go a long, long way back in both Wi-Fi, cellular, and the IoT standards as well. So I can tell you lots of stories. So with that, let's move on. So in this webinar, I want to tell you, basically, I want to build a bit of a story for you. And so it will give you a glimpse into the 802.15.4. And I'm going to show you some really in-depth technical information so you can kind of see what the protocol looks like. And I want to first talk about why it's so important to understand this protocol. And then I want to talk about and start building your knowledge. So my goal is to kind of give you a bit of an understanding so that then you can build from it. I obviously can't explain the whole protocol in an hour, but give you enough that you know where you need to go, where you need to learn more information about it. And then what I really want to do, which is really exciting, is show you why 802.15.4 actually meets a huge diverse set of very distinct requirements, right, in the market. And I think you'll be quite surprised by the protocol. And I'll draw some comparisons with 802.11 as I go through to kind of help your understanding. But remember that when I do a comparison, it might be conceptually similar, but it will be technically very different. So try not to draw too many conclusions if I compare it with the 802.11 Wi-Fi standard. Okay, so with that, let's talk about why this standard is so important. And as I mentioned, over 60% of the market will be using an 802.15.4 radio. So it is the leading one that's out there. And you can see here on this slide that it's going into just a huge diverse set of markets. So from your home network to smart buildings. I'm going to show you the industrial side a little bit later on. I'm also going to talk about some of the changes to support metering. So connecting your gas and electric and water meters using this standard. And so it's really in a lot of different markets. All of those markets have very distinct application requirements. And what I said was the exciting part of this webinar is I want to show you how 802.15.4 meets that diverse set of requirements. And you'll see the flexibility. And I think it will quite surprise you that's existing in this standard. Now, historically, most of the chipsets you would see would be all 802.15.4, but increasingly you're seeing chipsets now combined with Bluetooth Low Energy and also a Wi-Fi chipset, Wi-Fi radio into one chip, particularly in the home consumer market, smart buildings, things like that. Not so much in the industrial and metering environments. Okay, so what is 802.15.4? So for those of you that know the IEEE 802 as a standards body, their charter is only to define the layer 1 physical layer and the layer 2 MAC layer. They don't define, and their charter doesn't allow them to define layer 3 networking or above. They're focused just on the lower layers. So what that means is that what this defines, oh, I've lost my cursor, there it is. What this defines is between two nodes, it defines how they communicate, right? So it's a link layer protocol. and it defines how this node, node A, will talk to node B. Whoops, my cursor, I should have used black. I just can't see my cursor. Let me just change my color a moment so I can see my cursor a little bit better. There it is. And so it defines a link layer protocol, and then sitting on top of it, you can define other standards. And so what you'll find is that 802.15.4 has been used as the underlying technology that underlies technologies like Zigbee, Thread, Wireless HART, ISA 100, and YSUN. So when you think about those other technologies, they are providing the higher layers that then works on top of 802.15.4. And that is why it fits into all of those different markets and why it's so important that you understand this protocol, in my personal opinion. Right. So when we look, as I said, 802.15.4, just like Wi-Fi, defines a hop. And so it defines the ability to connect between two nodes. So if you want to form a network, a mesh network with multiple links, what you need to do is you need to have a higher layer protocol then to define the routing between nodes over multiple hops. So 802.15.4 is a link layer protocol, just defines the connection between two nodes. The higher layers then bring the networks together. And so you'll hear things like 6 LoWPAN, technologies like this, or RPL. These are IETF technologies. These are technologies used by things like Thread, ISA 100 to define then how they do the networking pieces. Okay, so everything we're going to be talking about is going to be the physical layer and the MAC layer. So when you look at the physical layer, and I'm going to talk a little bit about the frequencies that they operate on, there is a diverse set of frequencies that are supported by 802.15.4. So many people will be familiar with the 2.4 gigahertz band, but there are many other frequency bands as well. Some of them may actually be dedicated to certain markets. So years ago, for instance, I worked in the utility industry, and there are specific frequencies that are dedicated to that band. And so this technology could be deployed not only in unlicensed bands, but also in bands for specific industries. And you will see that in some markets. Okay, and I'll talk a little bit later on about how it forms a network and how you connect. Okay, I think I've said everything. Good. Okay, and wow, look at this. This slide, it looks a bit like 802.11, right? When you get A and B and C, and then you go into AA and AB. So the main thing you should be taking away from this is just like Wi-Fi, 802.15.4 has continued to evolve. And so it continues to add new physical layers, new MAC features in order to support new markets and new applications. This isn't a standard that was just defined years ago and it's just being used. This is one that continues to be evolved. And when we look at technologies like Zigbee, lost my cursor again, there it is, then you're going to be seeing these are the ones that they really focus on. And it was largely based on the original 2003 standard. In fact, the Zigbee Alliance was the organization that pushed it through the IEEE and made it an IEEE standard. But since then, you can see that there is applications around smart metering, and I'm going to talk about the enhancements done in G. You see some interesting new PHYs coming in, going after some of the industrial changes that are needed to support a much more reliable network that you'd want in and much larger networks. And you'll also see, look, TV white spaces. You'll see somewhere here, there's the railway, or here it is down the bottom, the railway communications. So it's going after a lot of really interesting architectures. And here you can see critical infrastructure here as well, and advances in security. So the main message here is this is a technology that continues to evolve and is very important in our marketplace. So now I've convinced you that you should care about it. I'm also a great believer in pulling down the specs, not to read them, but to use them as a reference. And I'm going to show you how you can do that in this webinar. And so the latest one, just like with Wi-Fi, they are periodically combine all the enhancements into one spec and publish it. And the latest one is 2020. And just like with the 802.11 spec, you can pull it down from the IEEE GET program at no cost. If anybody's not familiar with how to do that, I'm sure we could tell you. So not a problem. Okay, so the first thing I want to do then is to take a look at the physical layer, and then we will take a look at the MAC layer. So I want to give you some visibility into both of these layers. So the physical layer. So the first thing here is that it supports a lot of different physical layers. And this is not a full list, and those physical layers work at different frequencies. And so this is a good time to go and refer to the spec, right? And I love reading specifications. So, but again, I wanted to show you here. Here's just, this is general physical requirements. And you can see here that there is a huge number of physical layers that's defined. And why do we need so many different physical layers? Because we are satisfying very different markets. And so in a moment, I'm going to show you the most common physical layer used by Zigbee, so in your home or smart buildings. And then I'll show you what can be used for metering applications. And why do we need a different physical layer for metering? Well, think about it. I think how much further I have to go for a metering application. I don't want something that's going to go 20 feet or 30 feet. I need potentially a much greater range. So for that, I can use a different physical layer. So there are a lot of different physical layers in this standard. And don't think of it like Wi-Fi, where we have one physical layer and then we improve it and then we sell products with the latest physical layer. Think of this as having multiple physical layers and different physical layers for different applications, different solutions. Okay. And if I just scroll down a bit here on this page, you can see the diversity of different frequency bands. And you can see it'll go through and explain which physical layers operate in which frequency band. And you can see there is an enormous number of frequency bands. And so different markets around the world, like China, India, they have, there's been adjustments to allow this standard to be deployed specifically in their markets. Okay. Okay, let me just tuck that away. We'll come back to that in a moment. So these are the two that are most commonly used by Zigbee, which is one of the most dominant standards that's out there. And that's what they base it on. So based on the very early specifications. And here's my frequency band. Again, I prefer to use the specification for a full link. But here in the States, if you're using Zigbee in your home network, you're probably using the 915 band. If you're over in Europe, you might be using this band here, the 800 megahertz. And of course, we also have this deployed in our 2.4 gigahertz band, where we have our Wi-Fi networks. And of course, they will interfere with each other. Right. I'll talk more about that in a moment. Um, so this is a very detailed slide, and I'm not going to explain the physical layer to you and there's so many of them. What I wanted to do was to compare and contrast a couple, so you would get a feeling of what these look like and why would I use a different physical layer. So this is the one that's used by Zigbee networks, and it's a direct sequence spread spectrum. So if you remember, 802.11b was a direct sequence spread spectrum, and Wi-Fi then moved on to IRF-DMA. Well, IRF-DM and then IRF-DMA more recently. Now, direct sequence spread spectrum is a very simple radio. And so the advantage of having a direct sequence spread spectrum radio is I can keep my costs down low. And so an OFDM radio is normally about, well, years ago, it used to be about 15% more expensive. An OFDMA radio is even more expensive. So if I'm developing an application where I want to have low cost sensors, using direct sequence spread spectrum is a good idea. It keeps the cost down. What I wanted to point out here is the spread spectrum. So you have a spreading code. So like you have the Barker code in 802.11b, for those of you old enough to remember that, here you have what's referred to as PN codes. And oops, I'm sorry about this. I got some words on here I didn't notice. So it's called a PN code. And you'll notice that in the lower frequencies, I use a different PN code than I use at a higher frequency, which means these are different radios. So even in the same standard, these are different radios, the different PN codes, so different spreading features. And so don't think that even though you might think, oh, this is one physical layer, but it actually encompasses different radios. And this was particularly adopted, and you'll see that in the residential and commercial smart building environments. Of course, you'll also see it in the industrial environments, etc. I also wanted to point out that the data rates are different as well. So over here on the left, on the data rate column, you can see that the data rates are different. And the reason is that they are using different channel spacing. So in the 800 band, it's a very narrow channel, so the data rates are lower. In the 900 and the 2.4, they use a wider channel spacing, and that allows them to get to a higher data rate. Now, I mentioned that this standard can tolerate interference, so the spreading code allows them to work with Wi-Fi and still be able to recover those signals. So this is a very good radio. So as I mentioned, the channel spacing is different. So one of the things that you have to understand on this standard, unlike Wi-Fi, where Wi-Fi in the 2.4, you have channel 1, channel 2, channel 3, depending on your physical layer, you will have different channel bandwidth and a different channel number. So there's not one set of channels. You have to have the channel number. You have to know what physical layer you're using and what frequency band you're in. And then you'll know what the channel numbers are. And here I'm showing you what would be the Zigbee channels using the direct sequence spread spectrum orthogonal QPSK physical layer. And again, main point here is not to remember the numbers, but to understand that they differ for different frequencies and different physical layers. Don't expect one set of channel numbers like you have with Wi-Fi networks. Okay. Okay, so to finish up on our physical layers before I get going on the Mac layer, I wanted to show you the physical layers that were added in G and very much to support something like YSUN, which is going after the metering applications. And in particular here, you see a frequency shift radio. Oh, there we go, there's my cursor. And this is just, you know, if it's a 1, you shift the frequency that way. If it's a 0, you shift the frequency that way. This is a really low cost, simple radio. And look at the channel spacing. Look how small it can go to. right? And look at the data rates that it can go to. If all I'm saying is, hey, I use this many units of electricity, I don't need a lot of bandwidth. And I would like to support hundreds and thousands of meters. So I don't want wide channels. I want little tiny channels. And of course, if I'm little tiny channels and I'm very low data rate, what does that give me? Range. It means that my signal can go much further. So just like on your Wi-Fi networks, at the edge of the network, you get a low data rate. So if I want to get to really wide networks and to metering applications, I want to go to really low data rates. Pretty cool, right? So now you're starting to see the flexibility on the physical layer. Let's move to the Mac layer. Okay. So good news is that it's a fairly simple at the Mac layer. There is always a pan coordinator, right? You can think of it like a controller, if you like. And there's always one, right? And only one in one network. Typically, it would be powered on, right? So it's not battery powered, because if this thing isn't on, your network is not communicating. And what I need to do is I need to connect to the PAN coordinator in order to connect to the network. And that might require me to go multiple hops. So this might be me in a mesh network. My message might go multiple hops to the PAN coordinator before it comes back, and it will assign me an address, right? And so this is all defined in the Mac layer. And it defines two types of nodes, right? And so if this is my PAN coordinator, and this is my device that I want to connect, and I have to hop through multiple nodes, these intermediate nodes need to be capable of routing. And so those are full functional devices, a little bit more expensive. You may want to power them on the mains. You may not want them going to sleep, because if they do, they're not routing anything. But this little old end device here can be a reduced function network, not need a full protocol stack, not need to route, so I can keep the cost down really low. Okay, so that's the concept of keeping this Mac layer really simple. And with that, it can support a simple star network. You might use that in your home, for instance, where you might deploy a central controller, a bit like I was showing on this picture here, like a light, might be a light controller or something like that. And then you can have these other nodes that then connect. And what you'll find, I've got to watch time, but typically what happens is you want to power up your PAN coordinator, and then you connect all the other nodes to it, and you can very simple form these star networks, but it limits the distance. And so most networks have moved to these star configurations where you can hop across multiple nodes. And remember that 802.15.4 defines how the links work, how two nodes talk, but how it routes across the network is defined by your higher layer protocols like thread, wireless HART, etc. Okay, so getting into the fun bits now. How do I support all of those applications? So you've seen at the physical layer, I can do it by having lots of different physical layers, lots of different frequency bands, you name it, I can find an optimum physical layer for your application. But what do we do at the Mac layer? So the original standard 802 15.4 2003, when it defined the two physical layers used by Zigbee, also defined two mechanisms for access. What do I mean by channel access? How you use the RF, right? So how you're accessing and saying when to transmit, when not to transmit. And so there were two approaches in the original standard, and this is the one that's used by Zigbee. And you're like, oh my goodness, Avril, carrier sensing multiple access collision avoidance? That sounds like Wi-Fi, right? And yes, it does. And so it's the same concept. I listen, and if I don't hear anything, then I can proceed to the next step of starting my transmission procedure. So it's just like Wi-Fi in that way. Of course, the process is a little bit different, but it has, just like in Wi-Fi, you have SIFs and IFs and DIFs and PIFs to do the time intervals. You have time intervals here in this standard as well. So it's conceptually the same thing. What is more interesting, it's this Zigbee networks was called non-beacon. And I personally hate this name because it does not mean there's no beacon, right? There is a beacon. And just like in Wi-Fi networks, that beacon will tell you, hey, this is what this is my 802.15.4 network, and here's how I work. I'm going to show you the beacon frame in a moment. But it doesn't send it out on a regular basis. So in Wi-Fi networks, you normally send the beacon every 100 milliseconds. This one does not send it out. You have to request it. So when you turn on your device to find a PAN network, you'll make a beacon request. You'll go, hey, anybody out there? And then the PAN coordinator will respond back with the beacon. So it's called a non-beacon network. And Zigbee, all the Zigbee networks that are out there are based on that. Now, I'm going to show you the beacon enabled. And the reason is because this, although I'm not aware of any deployments of it, it was enhanced for the industrial space, industrial and the metering space. So this is an important one to understand, because later on I'm going to enhance it and I'm going to show you those enhancements. This is an alternative, and there are several alternatives. And again, if you go into the standard, because I do like to encourage you to look in the standards, and let me just type it in. I actually wrote it down rather than do a search on it. So if we go to 5.7.5.1, we should be able to find it. So, and you can see here, you can see the different access methods that are defined in the standard. Okay, and each of these are different. So how you access the medium will depend on what the application. Are you running, are you trying to do a home market? Are you doing industrial? Are you doing metering? Is it critical life kind of applications? You'll use a different method. And again, this is how it supports all of these different applications. Pretty cool. So I'm going to take you through and show you some of these. But the other thing that it does is it has information elements. So just like Wi-Fi, every time you add features to Wi-Fi, you add information elements to your beacon, right? N, AC, AX are all information elements added to your beacon. Same thing conceptually here. They're obviously different information elements, but the same thing. So rather than, so what it does is it says for these extra features that are needed for the metering environment or for the industrial environment, here's an information element, here's the extra things you need in the beacon to tell you about how this network works. So conceptually the same as Wi-Fi information elements, but supporting not extra features and capabilities, well, it's supporting extra features and capabilities, but for specific markets and for specific applications. So these are the two ways that 802.15.4 can do all of those applications, right? Pretty cool. So let's take a little look at this. So to start a network, you bring up your PAN coordinator, and the instructions will say this is the controller, and you bring it up and it forms a network, it gets an ID, and then any other devices will simply power on and then send this guy, hey, what's your beacon? I send it back, and then I can go ahead and associate with it. It's a very simple process. Normally you want to bring these things pretty close to it, get them to associate, and then you can put them in the network. You don't have to do that, but sometimes you do. Okay, so this is the method used in Zigbee. This is the beacon enabled. And you can see it's just like Wi-Fi. I calculate a random period of time. I wait the back off, sense the channel. If it's free during that time, I transmit. Just like Wi-Fi, the details are different, but same concept. This is what you use in Zigbee and Thread networks. The beacon ones actually are sending out a periodic beacon, and it will define how the medium is being used between the beacons. You don't do that in Wi-Fi networks. In Wi-Fi, you might send a regular beacon, but you don't say, here's how to use the RF between beacons. In beacon-enabled networks, you do. And so here's a picture where I send the beacon and I say, anybody can can talk to me here. We're using normal collision avoidance techniques. And look at this. I have guaranteed time slots. I can give devices specific time slots where only device A can transmit or only device B. And you're like, wow, guaranteed time slots. Don't see that in Zigbee. The problem is you could only have up to 7 in the original specs. So along came an enhancement specifically for large networks that says we need to do something bigger and better. So it extended this frame, and now you have multi-frames, and it extended the beacon interval. So not every frame is sending a beacon. So you can avoid beacon collisions in large networks. And so now I have the ability to dedicate resources to many, many more devices in very large networks. But get this, not only can I do that, but I can now use lots of frequency channels. So in Wi-Fi networks, you know, you've got an access point and devices, and they're all using the same channel. In these networks, I can deploy multiple channels. And so these devices, for instance, where's my cursor gone? There it is. A device here can talk to this one using one channel, and in the same network can be using a different channel to talk to a different node. So I can use all of the channels in the 2.4 gigahertz band, or all the channels in the 915 megahertz band. I'm not just using one in my network. So this allows me to connect many, many more devices. And I can now allocate resources, and I can say, hey, when device 1 talks to device 2, use this slot. And device 2, when you talk back to device 1, use a different slot. So now they can talk to each other, and they've got different slots assigned to them. Wow, how fantastic is that? And think about, wouldn't you want that in an industrial, in a more robust, where I need to have more deterministic network? Absolutely. And then look at this. Not only can I do that, but I can do frequency hopping. So when I'm transmitting, just like Bluetooth, I can hop between frequencies. So if there's a bit of interference, I can move on to another one, and it's like, wow, there's no interference there. So it makes it much more robust in very strong environments, again, industrial environments. This is really cool, right? And so let me keep an eye on time. Okay, I think I'm going to make it for questions. So this is one that was then like, oh, well, you know what? Yeah, we kind of improved that super frame structure, but why don't we just do something completely different? And why don't we define a new slot structure? This is ISA 100, right? ISA 100 did this. This is the group that drove that. And they said, you know, why don't I just have everything guaranteed? Why I don't need this collision avoidance stuff anymore. I'm running an industrial environment. Every node in my network, I want to give a slot. And again, here I'm just, and you can give different slots for different nodes in different directions. It's really, really cool. And again, you can do that on multiple frequency bands. So I can use all of the channels in my frequency band that I want to deploy for my network. It is really enabling me to get a lot of devices. And typically these time slots are about 10 milliseconds. I can still do collision avoidance, but I've now removed all the limitations and I can do guaranteed slots only if I want to, and I can mix them. So it's really very powerful. Okay. So the last thing then I want to talk about is information elements, right? So you know that the physical layer is very flexible because I have lots of physical layers. You know there's lots of different ways that I can use the RF because I have different access methods. What about the information elements? So this is your frame, your 802.15.4. You'll notice it's incredibly simple. I've got a very little physical layer. I've got a very simple MAC layer. Historically, for most networks, the payload is restricted to 127 bytes because I'm just sending very short amounts of information in a sensor network. It has been expanded up to 2K for the industrial environment. So the payload does vary, but it's very simple in comparison with a Wi-Fi network, right? Frame control sequence number, address fields, and a frame check sequence at the end. So this is a very simple protocol, keeps the complexity low, keeps my overhead low, makes me efficient and low cost. The information elements I wanted to show you, this is the beacon frame. And the beacon frame, and you can see it's carrying information about the super frame structure. So when I request the beacon or receive the beacon, I know how the RF is being used. And information elements have been added here to support different technologies. And one of the things I want to point out to you is that unlike Wi-Fi, you can add information elements not only in the MAC header, but also in the payload. So if you, for instance, are doing the first access method, the DSCH that I talked about, you would want to put that information in the header, in the MAC header. But if you were doing time slots, you would want to put that in the actual payload. So you have header information elements and payload information elements. And again, if I come back to my beloved standard, right, and I type in payload information elements, hopefully I want to try and see if I can get to the header of it. Yeah, so oops, I need to go up a bit more. Sorry. A bit more, but you'll see a bunch of information elements, just like you would in the Wi-Fi standard. Sorry, I need to go to the top of the standard. Sorry, let me see if I can do that again. See if it will let me without retyping it and put this in there. See if it will give it to me. Yep. Okay, I'll do that. Okay. And so payload information elements, there we go. And so you'll see a whole bunch of information elements, just like you see in the Wi-Fi standard. And this is a payload one. And so you'll see the TSCH one here. You'll see the other ones in the header information elements. So this is how, again, you add flexibility into the standard to meet all of these different application requirements. And you'll see new information elements being added all the time, just like you do and you see the list is getting very long, just like you do in Wi-Fi networks. Okay, whoops, got to give you some questions. So I'm done. I hope that gave you a good overview of 802.15.4, and you're all super excited to learn more.
I think so. Thanks so much, Dr. Salter. We've got a lot of good questions that came in while you were presenting. So,
Great.
and thanks again for joining us. We'll start with a question from Romac, who asks, do you know of any 802.15.4 technology other than Thread that will allow for IP communication?
Sorry, allow for what type of communications?
IP?
IP? Ah, so if I go back to that very first slide here, where was it? This one. Um, ISA 100, for instance, also supports all of the IETF protocols that are also used by Thread, specifically for the industrial environment. And I'm 99% sure that YSUN does as well, but it's been a while since I've looked at that standard and it's not freely available. So, um, there's nothing to stop having a proprietary, a company could create their own technology using this and not have it all standards based, but not make it publicly available. Like if you were doing a hospital application or something like that. But it's not just Thread, they're supporting IP version 6.
Yeah. Yeah, and I think
Yeah,
6LoWPAN, which is kind of a component of those,
yeah.
is it supports IPv6. Although I haven't seen just devices that are 6LoWPAN devices and networks. It seems to be a component of other solutions. Is that usually how it's used?
Yeah, so I actually had a hidden slide. I thought, oh, I don't have time for it. So let me just see if I can unhide it. So let me just unhide it so I can show it to you. I
Sure.
actually had one of those slides in here. So yeah, there we go. So I've unhidden it, so I should be able to get to it. Is such an interesting question. There you go. So this is how this technology actually works. And it basically is like, you think of it like a stub network, if you're familiar with IP stub network. So each of these can be a PAN access network, so a PAN. Um, and then it provides these edge routers. And of course, therefore, going here, you're using your traditional IP networks, be it IP version 4 or IP version 6. And so this is how you can create very large um, networks. And so, for instance, you might just make up some stuff. You might put this one on floor 1, this one on floor 2, this one on floor 3, or you could have overlaying things like you could have my lights are on this network and my temperature controls are on this network. And so you can build a very large mesh network. And then the actual routing protocol, typically this would use maybe a one-to-many or a many-to-one. So all these devices, they all send, many to one or one to one to many going in the other direction. So you can have some very simple routing protocols that don't add much complexity to the individual nodes within the network. Did that help a little bit?
Yeah, for sure. And maybe just I'll add to this new emerging standard with Matter supports IPv6 as well.
Yes, it does. So I've not worked on Matter myself, but if I understand it, you've got all of these protocols like this, protocols above it like RPL, things that are managing your nodes, etc. And then Matter kind of sits on top of it that then allows you not only to work on 802.15.4, but also, you could have a Bluetooth network. This protocol, there's actually a version of this protocol that works on Bluetooth and also on Ethernet networks. It's a different standard, but it's called the same thing, but it works on Bluetooth. And so Matter allows you that seamless application to work on lots of different radios. And it comes back to that point I raised at the beginning. I'm sorry, I always answer questions, very long answers. You'll get back on the question. But just to point out that it comes back to, where was that question here? When I said a lot of the chipsets now actually combine it and Matter. This is wonderful for Matter because it's giving you whatever your application, whatever your radio is. Of course, 802.15.4 is a much better radio than Bluetooth Low Energy and Wi-Fi for sensoring and metering type applications. You can
Great.
disagree with me there, Jim, if you wish.
I don't disagree with you, actually.
Uh,
Question here from Nick. He says, does 802.15.4 include scheduling so that it can offer SLAs with guaranteed latency and jitter?
No, it doesn't. However, if you look at ISA 100, which is running on the remember we talked about TSCH with the slots, the time slots, and every 10 milliseconds. Higher layers of that standard will provide some scheduling, and so they define an upper MAC layer, so it's still a link layer protocol, but it's not part of 802.15.4. It's part of the ISA 100 standard. I'm not sure about YSUN. I don't have access to those standards, so I can't talk about it.
All right. Question here from Fang, who asks, can you tell a little bit more about 802.11ah and the difference with 802.15.4 and their applications?
Oh, can you remind me what 11AH is?
Yeah, that's Wi-Fi Halo. It's the
Oh,
900 megahertz long range, low power amendment for Wi-Fi. And we're just starting to see kind of the early chipsets be released. A company called Morse Micro in Australia is doing a lot there.
mm, mm.
So it's
So, Jim, do you want to take a stab at answering that question? Because I'm not sure that I can. I mean, I'm assuming it's an OFDM radio.
yeah.
Um, um, but I'm not sure what the pros and cons are, other than it's an alternative competitive technology. But Jim, do you want to make a go at that technically?
I'll try. I think Wi-Fi Halo is very new, and it's not exactly clear what use cases it's going to be a good fit for. I don't see it disrupting or displacing 802.15.4, particularly with all the consumer market inertia behind that with the new Matter standard and others. But I think what you'll see is that it's kind of used to augment the capabilities of Wi-Fi devices. So when they're, um, hundreds of feet away from the AP, they still have an ability to maintain their IP link and do some limited, very low throughput communications. And that might open up some capabilities, in the home in terms of extending range quite significantly. And then in the enterprise for reasons there. So, but yeah, like Scott is saying in the chat, Halo is low throughput, below 1 megabit per second. So we'll see where it goes.
Yeah, yeah. Definitely a demand for these low data rate services. And Jim, as you're talking, I was thinking also the advantage of Halo would be it's got the same MAC as your Wi-Fi network. So if you are integrating the two, there may be some deployment scenarios where it works better than having a completely different MAC that you'd have in 802.15.4.
Yeah, and we haven't seen this yet, but I wonder if in the future there could be just a combined chipset that supports 802.11ax as well as AH. So we'll see.
Yep. Yeah,
And you know what? There's a really good question here, Heather, that I think we should give to Eric, as we can transition to him.
Shadows.
And thank you so much, Dr. Salter. A lot of compliments in the chat, and I really enjoyed the presentation too. So thank you.
Great. Oh, thank you. Thank you, everyone.
The question for Eric from Gary. He says, is 7Signal able to identify the protocols that are listed so that we can know the type of service in the 2.4 gigahertz band?
Wow. Okay. Well, that's pretty good. And you know what? I think this is a great opportunity. You're right. I couldn't be any more wrong. But you are right in that this is perfect for our little segment that we have now with just a couple minutes to go, 7 minutes with 7Signal, where we take a little feature inside 7Signal, unpack it, and show you how it can have awesome value. So let's take a look. I'm going to share my screen. And let's do this. And let's do this. And if you can see that, why don't you give me the thumbs up? All right, thank you. All right, so as you guys may or may not be aware, inside every single Sapphire Eye from 7 Signal is a spectrum analyzer. And so if you've got one of these Sapphire Eyes in these remote offices all over the place, or in this case, in our example today, these different stores all over the country, then you can actually have a window into whether or not you've got these competing protocols, right? 802.11.15 versus 11. Are they interfering with one another? I mean, who knows? Unless you have a Sapphire Eye and a spectrum analyzer to kind of show you what is truly going on. So check this out, guys. I'm just going to look at 2.4 because we're looking at all of the energy in the 2.4 gigahertz spectrum. And I want to look at a line graph as well as a waterfall chart. So what does that look like? There we go. Okay, so we're going to look at the line chart first. Each one of these lines, each one of the colors represents a different Sapphire Eye. Okay, and this is what I would expect to see in, from an overall standpoint, the 3 humps indicating channels 1, 6, and 11 in effect. And actually this gray one right here, you can see the rise, the Wi-Fi energy on top, and then the fall. But then look, guys, I also see something else that's rather peculiar. These are very peculiar shaped humps. You see this right here, this one? When I mouse over it, I can see that that's store 106. And when I look at this purple one right here, that's store 756. And that doesn't exhibit the same type of signature that I would expect to see. Not only that, but the line chart is also really good for helping you identify, okay, you see these spikes right here on the right, and then also on the left, and then also right here. This is going to be your BLE. We know because of just where they advertise, where they hang out and advertise. And so that's perfectly normal. But I'll tell you something that I don't like that doesn't look perfectly normal, and that's this jagged spiky stuff that's right in between what would be channel 11 and that BLE. You see this spiky stuff right here that's happening? Now, again, the reason why this is important is because if you're in a store or a location and you want to use IoT devices, if you want to use 802.11.15, Zigbee, or whatever it might be, or point of sale devices, you need to know if there's going to be some kind of interference. Otherwise, you're defeating the whole purpose of either using one, the other, or both. Usually, you just want to use one or the other. Now, let's just take one last look at what this appears to or show up as a signature when we look at waterfall. Okay, so here we go. Here's like the channel 1, 6, and 11, and you can see the streaky stuff going back and forth. That's going to be some other protocol. Not going to be your 802.11. Okay, and let's go down a little bit further. Look how hot to trot this signature is. And this is some of that stuff that we were talking about before with the scratchy stuff. This is going to interfere with anybody who's trying to use channel 11. Or if you're on channel 11, you're interfering with somebody who's trying to use maybe some kind of a Bluetooth or Zigbee device. And then here's another one here where you can see where the signature is lit up hot within the channel 11, indicating that there could be either that could be a Wi-Fi device or not. And so there you have it, guys. This one is really interesting as well. Look at that signature right there. That's really overlapping. So this is where I would say, you know, maybe there's some kind of IoT device in the environment that's overlapping and interfering with Wi-Fi or vice versa. And that's it. That's what I wanted to share with you guys today. Awesome stuff, Dr. Selter. Really appreciate it. And I just want to remind everybody out there that while you and me, we can't see or hear Wi-Fi, 7 Signal can.